Hello and welcome. In this video we are going to look at the current through lamps and diodes and how that changes when you vary the potential difference across those two components. We'll have a look at the lamp first, and how we might measure that is if we set up a circuit that looked a bit like this. So we have a cell, two cells, which we call a battery of cells. This is connected to a lamp and then back to the battery of cells via an ammeter, and we also have a voltmeter measuring the potential difference across the lamp here. Now this is how you might set it up in the lab, but a circuit diagram looks a little something like this. So what we have is our battery connected to the lamp, to the ammeter and back again, with our voltmeter measuring the potential difference across the lamp. Now we could measure the different current that goes through the lamp for different potential differences, and we would draw a graph with axes that look a bit like this. So we could change the potential difference here. We could go from maybe 2 to 4 to 6 to 8 and so on, and for every different potential difference we could measure the current and see how that changed. Now for a lamp, this graph would look a little something like this. So instead of going up in a nice neat straight line as we did for the fixed resistor, it's actually more of a curve, and the reason for that is because the resistance doesn't stay the same in the circuit throughout the experiment. What happens is when you increase the potential difference at the higher values, we get more heat, the filament lamp becomes hotter, and therefore we get more resistance in the lamp, and that has the effect of lowering the current that flows through the circuit. So if you've got a higher resistance, even if you increase the potential difference, it won't go up as quickly as it could do because the resistance has a lowering effect on the current. If we were then to switch over our battery so that now the positive side is on the other side and the negative side is switched as well, we would get another part of the graph which would fill out this negative region here. So this is negative, so this would be -2, -4, -6 and so on volts. We would still get an increase in current, but we would see a little minus sign in the reading, and that's to show that the current is going in the opposite direction, and that part of the graph would look a little something like this. So what you see is this kind of almost S-shaped curve for the difference in current for different potential differences across a lamp. You should be able to recognize this graph and give some level of explanation of why it doesn't go in a straight line like across a fixed resistor. The second one I want you to know about is the current through a diode. So this one now is a diode we're looking at. A diode looks a little something like this in real life. The circuit diagram would look like this. We've replaced our lamp or our fixed resistor with this diode, and current can only flow in one direction. So the graph for this would be a similar set of axes, but when we start increasing our potential difference, initially we don't see much of a rise, but after a certain value, a certain low value, the current will start to get higher and higher as you increase the potential difference. So this part of the graph looks a little something like this. Now if we were then to flip our battery again, what would happen is we would get a negative potential difference. That would encourage the current to flow in the opposite direction, but as we know, our diode won't allow current to flow in that direction. It won't allow current to flow backwards, so therefore no matter how much you increase the potential difference in the reverse direction, the current would stay at 0. So a diode is a kind of device that allows current that only flows in one direction, and the graph of its action, or the graph of how its current changes against potential difference, looks like that. So really, in summary, we've got three graphs. This is for a fixed resistor. A fixed resistor would look like this in a circuit, and the graph goes up in a linear fashion, and what we say is the current is directly proportional to the potential difference. It's slightly different for a filament lamp, because the filament lamp will get hotter at the higher potential differences, and that affects resistance and therefore affects current. And for our diode, we'd get something that looks like this. So you should be able to recognize these three graphs and match them up with either your fixed resistor or your lamp or your diode, giving a little bit of explanation for each one as we've done over the previous couple of videos. Now the last thing I want to go through is on the higher tier, and it's to do with current through lamps and diodes, but actually more to do with the effect of temperature on current, and you should be able to explain how raising the temperature, or why raising the temperature, has an effect on the current. So here we have the atoms arranged in a metal conductor, maybe in a wire, and we know that the atoms are arranged in nice neat rows and columns, and when a current is flowing, we know there are electrons that are flowing through the circuit. So these electrons are happily flowing through and in between and around the metal ions or the metal atoms, and that's what we mean by the flow of current. Now what happens when we heat this metal is that the atoms, or sometimes you can call them ions, they get hotter, and when they get hotter they gain energy, and when they gain energy they vibrate more rapidly than they were doing previously. So what happens is we get some vibration, and I know they're not all vibrating, but I think you get the idea, and they vibrate more and more as the temperature goes up, and because they vibrate more and more, this causes the electrons to collide more frequently with the atoms, because they are moving much more rapidly or vibrating much more rapidly than they were before. And because we have collisions of these electrons with the atoms, the current gets lower. So let's have a look at how we might explain that. We've got free electrons flowing when there's electricity flowing or electric current flowing, and if we heat up the metal, what happens is as the metal gets hotter, the atoms, or ions you could say, because we know that these are technically can be described as ions with missing electrons in metals, but we can say as the metal gets hotter, the atoms or the ions gain energy. That causes the atoms or ions to vibrate faster or to vibrate more, and that means the electrons collide more often or more frequently. This is specifically how you should explain that idea there. You shouldn't say things like the atoms start to vibrate, because they're already vibrating even if the metal is quite cold. When we heat it, they vibrate more. That bigger vibration causes more collisions between the electrons and the atoms, or the electrons and the ions, and that reduces the current that can flow. So that basically explains why when we raise the temperature of a conducting material, a metal, the current goes down. Now that's basically an overview of the current across our lamp, across our diode, and an explanation of why temperature has an effect on current. That's me done for this video, and I'll see you again soon.